Hi everybody, welcome back. This is Unit 1, Lesson 11, and today we're going to talk about heating and cooling curves. So as you can see in your notes in section 12, you have an example of a heating curve. Pay attention to a couple things. Temperature is on the y-axis and energy is on the x-axis. Also, sometimes that's time, usually in minutes. You have a graph that looks something like mine, except you don't have points labeled. So I'd like you to right now go ahead and label your points. And so if you put here, call that point A, right here we'll call that point B, and just go ahead and write on your graph A, B, C. We'll call this point D, this point E, and this point F. Okay, so it's easier just to talk about the curve when we have the points labeled. So imagine we're starting with ice. And it is a solid, and its temperature at point A is at minus 40 degrees. Okay, so point A, we have a solid at a given temperature. And so from A to B, segment A to B, we heat up the sample. So you should recognize, according to the graph, that as you heat up the sample from A to B, the temperature increases. The temperature goes up, okay? As the temperature goes up from our test and from our last section of notes, you know that the molecules move faster. So if the temperature is going up, the kinetic energy, or the average kinetic energy of the particles, is going up. I'm not going to write out kinetic energy anymore. I'm just going to write KE increases. And since all the heat or all the energy that's being added is used to make the molecules move faster and faster and faster and faster, none of that heat is being stored. So we say then that the potential energy is constant. We're not changing it. Nothing's being stored. It's not going up, it's not going down. And again, I will use potential energy this time but next time, I will change it to just PE, because that's easier to write, and we kind of have a lot to write here. So we're starting here on our curve. We heat the sample. It goes hotter and hotter and hotter and hotter. The molecules move faster and faster and faster and faster until something significant begins to happen at point B. And at point B, we begin to melt. Okay? So the temperature at which that occurs is known as the melting point. And for this substance, it would be 0 degrees. So point B is the melting point. Okay? Point B is the melting point. Okay, so point B is the melting point, and that's when melting begins. Now notice, from B to C, so segment B to C, we're still adding energy. We're still adding heat during that segment. But the temperature stays the same. The temperature is not changing. And if the temperature is not changing, neither is the kinetic energy. Because when I say temperature, you should automatically think in your head, like a word association game, kinetic energy. Temperature, what are you thinking? Should be kinetic energy. Try it again. Temperature, I hope you're thinking kinetic energy. So if temp is constant, kinetic energy is constant. So where the heck is all that energy going? Where is all that energy going that's being added during BC if it's not being used to heat up the sample? It's like adding heat, but the temperature is not changing. It's kind of weird. It's being stored, okay? So the potential energy goes up during these flat parts of the curve when the temperature is not changing. The potential energy goes up. It's being used to store and break the intermolecular forces of attraction that exist in the solid phase. At point C, all the melting's done. Okay, so you have only liquid now, and from C to D, you heat the liquid. So point C, we'll do segment C to D. You heat the liquid. And you can see that the temperature goes up from C to D. And if temperature goes up, what else goes up? Were you right? Kinetic energy goes up. And the potential energy is the same. So we're heating the liquid, we're heating the liquid, we're heating the liquid, we're heating the liquid until something significant begins to happen. Remember, as we heat the liquid, the molecules move faster and faster and faster and faster until eventually they get enough energy that they can break free of their forces of attraction and start to turn into a gas. So point D is known as the boiling point. That is where boiling begins. At point D. And again, for this substance, it happens to be 100 degrees Celsius. Notice also from D to E here. I don't like that color. So from D to E, the temperature is constant while it's boiling. Therefore, the kinetic energy is constant. And all the energy that's being added is being stored. So the potential energy increases until every single liquid molecule has been turned into a gas, and that is when the boiling is done over here at point E, and at that point we heat the gas. Okay, so point E we have only gas. We could say the boiling is done. And so from E to F we just heat the gas. And we increase the temp and increase the kinetic energy, but the potential energy is constant. Okay? So on the diagonal parts of the curve, you have only one phase, just solid from A to B, from C to D, just liquid, from E to F, just gas. But what about those flat parts of the curve? On the flat parts of the curve, you have a physical change happening. You have a phase change happening. So from B to C, the solid is turning into the liquid. You have both phases present on that flat part, phase change. And from D to E, on that flat part, you have liquid turning into a gas, a different phase change on that part. So the flat parts represent the phase changes. Not that hard to remember. So in summary, on a heating curve, we can make two boxes on our paper. We have a diagonal part and a flat part. So let's say what's true on all the diagonal segments. On all the diagonal segments, we are heating only one phase. The temp is going up, and if the temp goes up, what else goes up? Kinetic energy goes up. But the stored energy is constant. Potential energy is constant. On the flat parts of the curve, we have a phase change. There are two phases present. Depends. The first one's the solid to liquid, the second one is the liquid to gas. And the temperature isn't changing, that's why it's flat. The temperature is constant. And if temperature is constant, you know what else is constant? Because they always do the same thing. Kinetic energy is constant. So where's all the energy going that you're added? It's being stored or adding. And stored energy is potential energy. So that is increasing. Okay? We also have to talk about a cooling curve. And basically it's similar except you're cooling. So you're not adding energy, you're removing energy. These ones, removing energy, losing energy, these are exothermic changes on a cooling curve. Heat is being lost. So these changes are exothermic. Notice the differences. You start hot and you end cold, right? So from A to B, again, you don't have the letters. Oh, you have sort of the letters. You have like little segments here, okay? So you have segment A on yours. A, you're cooling the gas. You can go ahead and label this. This is just gas. Remember, the diagonal parts are only one phase. This is just liquid here. And I believe you'd have another one, right? That is just solid. I'd like to see, I don't think I have the same one as you. No. Okay? So you're cooling a gas in segment A. You start at 450. Again, yours looks a little bit different than mine, but it's the same idea. So you cool the gas, you cool the gas, you cool the gas until, and again, when you're cooling the gas, look at what's happened to the temperature. The temp decreases, and if temp decreases, kinetic energy decreases, and if kinetic energy change, potential doesn't. So potential is constant. So you cool the gas, cool the gas, cool the gas until the molecules get slower and slower and they start to clump together and turn into a liquid. So this represents the CP, the condensation point, okay, of your gas. So from, during your thing, segment B, on mine it's from B to C, at segment B, you're cooling the gas, all the gas is turning into a liquid. Okay, we call that condensation. It's a flat part, it's phase change. The temp is constant. So the kinetic energy is constant, which means the potential energy must be changing, and on a cooling curve, it's decreasing, okay? At segment C in yours, this is your segment C right here. In segment C, we're cooling the liquid. You should notice what happens to the temperature. Look at the curve. The temp decreases, which means the kinetic energy decreases. The potential energy is constant. Okay? Segment D, it's flat. This is your segment D right here. It's flat. What do you think that means? It's a phase change. So for segment D on yours, we cool the liquid, we cool the liquid, we cool the liquid until the liquid begins to freeze. That's our freezing point. So segment D, the liquid is turning into a solid. It's freezing. And what's happening to the temperature on that flat part? The temperature is constant. And so you should know the kinetic energy is constant and the potential energy is decreasing. And then you probably already figured out what's happening in segment E. You are just cooling the solid. Okay, the temp is going down, the kinetic energy is going down, but the potential energy is constant. So again, just to summarize, on a cooling curve, in summary, on the diagonal parts, you have only one phase. The temp is decreasing, the kinetic energy is decreasing, and the potential energy is constant. On the flat parts, you have two phases because you're in a phase change. Okay? The temp is constant. That's why the line is flat. The kinetic energy is constant. And the potential energy decreases. Potential energy decreases. All right, folks, I'll check your notes in class tomorrow. Have a great night, and we're doing a lab, so make sure you're there. Bye-bye.